Question 3. The diagram shows a uniform magnetic flux density B in the plane of the paper Q. In the plane of the paper. Q and R mark the points where two long, straight, parallel wires carry the same current, I, in the same direction and perpendicular to the paper. The line through QR is at right angles to the direction of B. P is a point where the resultant magnetic flux density is 0, i.e. it is a neutral point. P is closer to R than to Q. Okay, so at P, we're going to have 3 magnetic fields acting. We've got the external magnetic field labeled as B, which we know is pointing upwards. And then both Q and R are going to have circular magnetic fields around them, but we don't know which way they're going yet. So I'm just going to draw in a dotted line that's roughly circular through both. Let's use 2 different colors like this. And as soon as we do this, we can see the one from Q is weaker than the one from R. We're further away from Q than we are from R. So question A says, explain whether the direction of the current I is into or out of the paper, and sketch a diagram that shows the direction of the different magnetic flux densities present at P. So we want the combined effect of Q and R's magnetic fields to be downwards to counteract this. And therefore, we definitely want R's to be downwards at this point in space. Remember, R's magnetic field is going to be bigger than Q's. If R's is downwards, Q has to be upwards, but Q is going to be smaller than R. So R's one is going to give us a downwards term to counteract the external magnetic field. Now, using the right-hand grip rule to get R's current to be R's magnetic field to be anti-clockwise, we need the current to be going up out of the plane of the paper. So that's the first point. So the current is out of plane of the paper. I know we all do this on our screen, but we still talk about the plane of the paper. So the current, if we could see it in both of them, would be coming straight up towards us. Sketch a diagram which shows the directions of the different magnetic flux densities present at P. So I'm going to use the system that I've just kind of started using here. So at P, we've got a magnetic flux density straight upwards. This is caused by the external field. Then we've got a magnetic flux density from R that's curving around this way. So at P, it's straight downwards, but the overall shape of it, and this is from wire R. And then we've got the other one, which is from wire Q. Let's use this purple color. So wire Q, also right-hand grip rule, so it's going to be going up, but it's going to be much weaker than the one from wire R. So that's wire Q. And what it tells us is at point P, these 3 do add up to 0. So I think that's a reasonable diagram to show it. If I is increased slightly, will the neutral point move towards R or towards Q and explain? So the field around a straight wire B is given by mu naught I over 2 pi R. So increasing I in both will cause them both to get bigger. By the same amount. Okay, so if we doubled the size of the current, we double the magnetic field strength of each. But doubling the magnetic field strength of each would mean that we had a bigger difference between the two of them. So the difference now would be too big when they're this far apart. So perhaps the easiest thing to say is, if these two had incredibly strong fields, much stronger than the Earth's magnetic field, then the neutral point would be in the middle. So any increase in the current is going to move it towards the middle. Whereas if both of them were very weak, the neutral point would go over towards R. There's a second neutral point on the line through QR. State giving reasons whether it is to the left of Q, between Q and R, or to the right of Q. So we'll quickly sketch out this diagram. Q and R. So remember, we're looking for a place where the resultant of the field from Q and R can be downwards, so it can counteract this external field B. So we know there's one about here. So where R has a big downwards one and Q has a small upwards one. If we come to the right of R, we're always going to be closer to R than we are to Q. And so the resultant on this side is always going to be upwards, however far we go. R's field is going to dominate out here. But if we come to the left of Q, we're going to be closer to wire Q, and therefore its downwards field is going to be stronger than the upwards field from R. So R's downwards as well, isn't it? So out here, both fields, the field from Q and the field from R, are acting downwards. So as we go away from here, both of them get weaker. We must eventually get to a point where these two fields add up to be equal to B. So the second neutral point is going to be somewhere to the left of Q when we look at this one.